Let's get started. So my name is Charles Bailey. I work for Bloomberg in London in developer experience. If developers have an experience they don't like, sometimes they come to me. Today I'm going to talk about x86 assembler. And my first disclaimer is I don't write any as part of my job, which is great for pretty much everyone. Unfortunately, I don't have very much time, and I'm going to get onto some code as soon as I can. So really, with this short time, it's not really about enough x86 assembler to be dangerous, but enough 86 assembler to be very dangerous. OK. How did I get into assembler? Well, a while ago, I had an ARM-based computer. So I don't know if anybody else has used Acorn Archimedes. No, right, OK. So the Acorn Archimedes had 4 megabytes of RAM, ARM2 processor, or at least the version that I did had, and it had a great basic interpreter, and it was very fast. And I had a lot of fun as a kid developing for it. And one of the things I wrote was a maze game. So you think of 3D graphics these days, it's really amazing. Textures, everything. None of that, absolutely none of that. It was basically 90-degree corners, step, 1 unit at a time, and render a big corridor. And what I was finding is that my basic program was really cool, but I had to learn about sort of this cool mode shifting technique where you could draw on a screen that wasn't visible yet, and then switch, because it was so slow it looked a bit funny if you were drawing it. And I actually had a please wait sign. I also had a subscription to a magazine which had lots of interesting stuff, and some of the stuff was how to write ARM assembly code. And the basic that came with the Archimedes actually had an assembler with it. So I kind of learned that. And I didn't rewrite my whole program in assembler, but I did take that core loop that was taking a long time, and I translated that, or transcoded, or rewrote it in assembler. And the speed increase was just phenomenal. I couldn't believe it. So I was pretty hooked there. But I hadn't really heard of C at this time, or C++. But one of the magazines came with a review of Acorn's C++ development environment. And it took me about 3 reads of the article before I worked out what on earth this thing was and what a different programming language could actually mean. But the cost, hundreds of pounds, was just like phenomenal. I mean, as a kid, it's kind of like, I don't understand why you buy something and then have to learn a new thing to do stuff I can already do. So anyhow, it's a bit about history of me in assembly language. And one thing that's really cool is like ARM assembly is now back in again. Cool. So why might assembly language be dangerous? Well, even if you don't think about writing it, a lot of people kind of look at assembler and kind of scratch their heads and try and interpret something from it. And one of the things to note is that assembly language is actually a bit further away from object code than you might think. So it's quite easy to write some assembler and assume that the assembler just does a mechanical translation. But that's not quite true. There's quite a lot of intelligence still in assemblers. So if you write mov, for example, does anybody know what mov does in most assembly languages? Yeah? Sorry? I see.
We'll take that from a register to a register or from memory to another.
It doesn't move, it copies. This is C++, CppCon, right? And we can't tell the difference between copy and move. So yeah, but it's just a data copying instruction. There are actually about 14 major opcodes in Intel x86, depending on the size of the register you're moving, whether you're moving it from memory to memory, between registers. You've got MMX instructions, SSE, SSE2, 3, 3 plus, or whatever, no, 3E. I can't even remember. There's an extra S at the front, isn't there? So there's a whole lot of stuff that goes on. So some of those have different extensions that mean something, some of them don't, and just depend on the operand. So the assembler's doing kind of quite a lot there. Similarly, if you've got jump instructions, jumps are always kind of relative. If you're jumping a really short distance, it can be quite a short instruction, just a couple of bytes. If you're jumping a bit further away, that can be more bytes. And the thing is like, the size of your code is now depending on what the assembler's chosen for these different things. So if it's managed to choose some quite short instructions, then suddenly a jump that might have not quite fitted in the shortest possible jump might suddenly now fit. So do assemblers need to take a second pass? Some of them do. So it's actually kind of there's quite a bit of difference between assembly language and object code. So the next myth is that chip manufacturers kind of like hard code their silicon to execute object code. And that's just not true. So it's just mind-boggling, the complexity of like a modern, well, not even desktop, but even a modern processors in your phone. They're just mind-bogglingly complex. And you can tell that this can't be true because Intel released microcode updates which affect the way that these CPUs execute object code. So sometimes they fix performance issues, sometimes they fix genuine bugs. Fantastically complex machines. So really, when it comes to assembly code, you can't kind of like look at it and say, oh, I can see, it's 2 instructions, it's going to be pretty performant. There's no substitute for measuring still. Okay, what about writing assembly code? It's like there are so many pitfalls, it's untrue. Every time I kind of look at some compiler-generated assembler, I normally see something that I don't quite understand. If I do the research, I see yet another pitfall. And these pitfalls can be, performance pitfalls. If you do this, it's not as performant as another way of doing it, which is less obvious. Or sometimes you actually hit, revisions of processors that have bugs. So, if you use some situations, if you use a single byte kind of return, there's some pipeline issues that mean that can be missed. You can actually get kind of bad code. So you end up having to use like a longer thing than is strictly necessary, and that can seem quite odd. So it's so complex that the summary is don't. But it is quite fun to do anyway. So I once was doing a challenge against a friend, and we were doing a poker hand evaluation. He did some stuff in C, and I had to look through all of the SSE instructions I could find, and I found some really cool instructions. You can do parallel adds and ORs and things, and I came up with sort of really cool ways to determine whether you had 4 of a kind or if you had a straight, because you can like shift everything across and like and it down and see if you've still got some non-zero stuff. So you can actually kind of like design really cool algorithms just based on some of these kind of quite obscure and cool opcodes. The sort of thing that's actually kind of difficult to do in C++, even if you know there are intrinsics around, it's kind of tricky. So if you shouldn't write it, and you've got to be careful with reading it, and it's not substitution for actually measuring performance, why would you want to learn assembly language? Well, the keynote this morning is kind of like Björn said it sort of better than I could. It's kind of like you should really care about what happens in the next level down, because without some understanding of the things that the layer you're working on are built on, you're not going to have a deep understanding of how things work, what makes things better. You can also learn about some of the trade-offs that happen under the hood based on the code that you write. So if you choose a different way of doing something, how does that affect the performance? You have to be very careful looking at assembler code. But in general, if you write some C++ that causes some code not to be generated or not to be executed, it's generally faster. You have to be a little bit careful. I wrote some assembly once, and I was removed a totally redundant instruction, and the performance went down. I was stuck on that for quite some time. Turned out what I'd done is I'd failed to put some data later on in the program in a different section. So it was actually just straight in the code section. And in the original version, it just happened to be aligned, so it was a really fast load. I removed a couple of bytes of instructions, and suddenly my code was misaligned, my data was misaligned, and the whole thing performed worse. So it's another pitfall to avoid. Good thing about writing assembly language, you always never have to worry about line length. So if you've in a company which 80 characters, assembly, it's never going to worry you. You never need to feel guilty about using a goto. In fact, a goto is so ubiquitous that in ARM assembly language, the opcode is a single character. It's just the letter B. for Bloomberg. The branch. But mostly it's fun. I do code because it's fun. Even C++, but cool. Annoyingly, the clock on my presenter display hasn't started, but we're going to get onto code pretty soon. In order to get on code, I'm just going to do enough architecture to get by. And what I mean by architecture is just a model of the computer as it pertains to the to your program, to your assembly program that you're writing. Sorry, the assembly code that you're looking at. We're not writing assembly code. I've recommended against that, haven't I? Okay, so I'm just going to talk about three things: registers, your virtual address space, and the stack. So registers are very fast memory locations, and they're the things that can be sort of directly manipulated by the CPU. You can't point to a place on silicon where they are in these modern CPU architectures. They do cunning stuff like register renaming, so some move instructions don't actually do anything. But in the assembly code, you can think of a register as just a really fast location to temporarily store stuff. They're tied to a particular CPU core, so if you're in a multi-core environment, the registers are local. You can't view another CPU's registers. They can't be interfered with. That's kind of part of what makes them fast as compared to a memory location. I'm going to talk 32-bit assembler because I'm kind of short on time. It's simpler. There are basically 8 so-called general-purpose registers on the x86. On the 64-bit, you get all of these, but prefixed with an R, and they're twice as wide. And you get another 8 as well, which are imaginatively named R8 through 15, I believe. Yes. They're called general-purpose registers, but that's not really true because many of them have special purposes. So the most obvious one is ESP, which is the stack pointer. You've got to keep that as a stack pointer. You could just assign it another value, but that's probably a bad idea because there are some instructions that implicitly use the stack pointer, particularly push and pop, and then various other variations on push and pop if you're going to MMX registers or other places. EBP, the base pointer, it's used in functions as a record of what the stack pointer is when you got into a function. So you can think of the range between the base pointer and the stack pointer as kind of local variables, kind of. It's not quite that strict. EAX is very important. That's used as a return value for short return values, so ints, pointers, and things. And then various other ones have got kind of specialties like ECX. There's kind of loop instructions that sometimes use it. Some calling conventions use ECX as the this pointer. But yeah, ESP, EBP, and EAX are the kind of most special purpose. It's a simplification, anyway. And then there are the true special purpose registers. There are kind of 2 obvious ones. There's the instruction pointer, which is prefixed with E or R, depending on whether in 32 or 64-bit mode. In ARM, it's known as PC, the program counter. It's all the same thing. You can't generally write and read from the program counter directly. You said you use kind of like different instructions. So if you call a function, use the call. That will cause the instruction pointer to jump to the location that you're calling, and execution will continue from there. You can then actually examine the stack because when you call, a return address will be put on the stack, so you can tell what the instruction pointer, what value it had before the call as well. And then there's the flags registers, and the flags registers are really about the kind of most used for conditional stuff. So flags tend to get set on arithmetic and logical operations like and subtract, and you can get things like the carry flag and the 0 flag, and then you can test them subsequently. So there are the most popular conditional instruction are the jump instructions. There's a whole lot of jump instructions that can be conditional on flags. So you can test whether some value is less than another and jump to a particular location if it is, just carry on executing if it isn't. Virtual address space. So pretty much everything that isn't kind of registers that you read and write from is something in your virtual address space. And these days we have the luxury of flat memory models, so we don't segment things up a bit. So all of your code tends to get an address in the address space somewhere, and then other stuff too. So dynamically, so your code is mapped in from your executable, so you can static data as well. Then when you dynamically allocate stuff, that also goes into your address space somewhere. And then finally, the stack also lives somewhere in your virtual address space. And you can just read and write locations from your virtual address space as you see fit. Generally, stuff that's mapped in from executables can be kind of mapped around the address space somewhere. Stuff that's kind of dynamically allocated, it tends to get kind of like mapped from low addresses kind of upwards a bit. And the stack tends to kind of be like a high address thing. And there's lots of kind of headroom to allow the stack to grow. So I'll talk about the stack now. Well, there can be multiple stacks in a program because it's specific to a thread of execution. Oops, I think I double-clicked there. So you've probably kind of looked at a call stack in a debugger, or at least watched some poor luckless colleague look at a call stack in a debugger. And it's kind of, just a list of function calls. In x86, as with many architectures, the stack is actually a kind of combination. So it contains return addresses, so it contains the call stack. It also contains parameters that get passed into functions, and it also contains local data. So if you kind of create some local variables, they're also kind of on the stack. And the really confusing thing about the stack in the Intel world, and actually, to be honest, quite a lot of most architectures perhaps even, is that it grows downwards. So you push something onto the stack, and that becomes the top of the stack, but that will actually have a lower address than things that were pushed further ago in time. So top of the stack, low address, bottom of the stack, high address. It's confusing and irritating. Okay, cool. I know what you're saying. You're just desperate to see some assembly code. So I came up, so how do you do this? Actually, who's heard of the Godbolt compiler explorer? So yeah, cool. That's a really great way to look at this. And of course, Matt Godbolt's here doing a talk. I think it's on Friday, so that should be good. But I was on an airplane not so long ago without any network access, so here are alternative ways of doing it. So mainly do this sort of stuff on Linux. Objdump, you can give it the -d to disassemble, and if you give it the -m Intel flag, it gives you the Intel syntax. There are two kind of common syntaxes for x86. I always try and go for the Intel because it matches Intel's documentation. You can tell your compiler to generate assembler instead of generating objects, so the -S. And again, you can give it a hint not to give you AT&T syntax, which is the other one. And if you're in a debugger, so in GDB, you can just type disassemble, it'll disassemble the current function. If you're on Windows, so I was playing around on my Windows machine, and you have Visual Studio, it's even easier. You just kind of open the disassembly window. Once that window has focus, your step in and step out happens at the assembly instruction level. It's really cool, really easy to use. So here's a simple example. Here's a function that adds two numbers together. I gave it a basic G++ invocation to this. When you generate assembler, there tends to be a whole lot of noise, very important noise for handling things like exceptions and position-independent code. Well, to be honest, on 64-bit stuff, the position-independent code you get for free, but on 32-bit, there's some clutter involved with that. So if you just pass these short options, you get some nice, simple assembler. Cool. So that's actually kind of pretty readable. So the first two instructions there are a standard kind of prologue for maintaining your stack. So generally what happens is every function records the stack at the beginning of its function in the base pointer, that's EBP. And then when it calls the next function, the call will store the return address, so the address of the instruction following the call, on the stack. So what these two instructions do is set up what's called a new stack frame. We're saving what the base pointer from the previous function, and then we're recording the value of the stack pointer in our base pointer. Okay, time for a diagram. So on entry to a function, this is roughly what things look like. So my function is executing, and the top of the stack is going to be the return address I'm going to go back into. The base pointer is the previous function stack pointer after it saved the base pointer of the function that called it. So you can see the loop back. That's a base pointer pointing to a previous function's base pointer. And what those two functions I showed on the previous slide are going to do is form that loop back, so that so I'm going to push the base pointer, so the stack pointer will move down one, and then into that new location we're going to store the value in EBP, which will then kind of effectively point back to where the EBP pointer is at the moment. So you can see that the stack is containing different sorts of pointers. So you've got the pointer of the return addresses that point into an area of code, of executable code, and then you've got the kind of the base pointer chain that points back towards base pointers of previous functions. And this is what kind of gives you the ability to walk a call stack normally. Now, I'd like to say things are not this simple, but this is actually takes a bit of getting one's head round anyway. It turns out that debug information, so modern debug information, is so rich that you don't always need to store a base pointer. So you don't. So you can get from debug information your call stack. So some compilers will just like omit this this jumping around, but because I'm using -0, no optimizations, we've still got this. So first two instructions are about setting up the frame pointer, and then the bottom two functions are essentially just undoing that. So I've saved the previous function's base pointer, and at the end I pop it off the stack back into the base pointer, and then I return to my callee. And then the rest of those three instructions are the meat of it. And all it's doing is again, the stack contains data. One of the things that happens before I get called is the parameters for me to get pushed onto the stack. So EBP +8 and EBP +12 are the two parameters. They get moved into two registers, EDX and EAX. So it's the move instruction in Intel syntax. The destination is the first parameter. So I'm moving the parameters into EDX and the next parameter into EAX. The add instruction is like a plus equals. It adds EDX onto EAX. And EAX, as I mentioned earlier, is used for the return value for short things. So there it is. It's in the right place. And so when I return to my caller, that answer is in EAX, the correct place. Cool. How long have I got? Cool. Excellent. So C++ is a CppCon. So finally, I get to do just a little bit of C++. I've got a demonstration class here. I believe that Nico Jasutis is doing the nightmare of move semantics for trivial classes. So go to his talk to find out why all of this is a bad idea. But one of the things that I kind of like looked at before is like often we're taught to implement operator plus in terms of operator plus equals because you can reuse code and make things simpler. But how should we do this? So here are two possible candidates. Does anybody want to vote for the top one? And who wants to vote for the bottom one? No, you're all on the fence, really. OK, so it turns out that the top one, I can fit the code on a single slide. I've demangled a couple of things. So you can see that there's a copy constructor. That's unsurprising, because if you look, I create a temporary. I then do a plus equals, and I return it. So that's cool. So I've got a copy constructor, and I've got an invocation of plus equals. So candidate 2 is interesting because it does pretty much the same thing, but afterwards it has more stuff. It has another copy constructor and a destructor. It creates an extra temporary. Does anybody know why that is? So, so why does that not happen in the second example? Yeah, do you know why? I mean, why it doesn't?
I think it returns name variable.
Yeah, so it returns a name value, but you can still have a return value optimization even without a name. Yes?
There's two temporaries, so it has to construct and destruct both of them after bringing out.
Yeah, so I mean, the key thing is that the operator plus equals returns a reference. Now, by convention, that reference is to the this that's passed in, but there's no way for the compiler to know that, so it has to create another temporary, which is kind of annoying because the bottom one looks neater. At least I think. I could go through and this line by line, but that's probably not going to be helpful. So there's a few minutes for questions. Yes? Do you want to should we use them? Or I can repeat the question.
So when I go into Godbolt and write some code, I see the assembler on the outside. Like I saw like the move, push and pop and all that from like assembler class in college, but it's always like move L, move Q. Like there's always these little like additions to the end. What are those?
Okay, so when looking at Godbolt, you're saying that you're seeing a lot of suffixes on the mnemonics. Gosh, that's a horrible word. I've managed to avoid it all along. So the thing like mov is a mnemonic, which gets turned into like object code opcodes. So it depends on the syntax you've been looking at. So if you're looking at AT&T syntax, the suffix is generally a way of saying what size of operand you're looking at. So L is kind of long. Anyway, it's 4 bytes. W would be just a 2 bytes, and Q is a quad word, so 64-byte length. However, you have to be slightly careful because if you look at the Intel reference manual, the mnemonics have variable length. So there's mov, but there is also, I believe mov Q is actually, there's a mov which got an extra letter, which is an SSE mov, and it isn't just a suffix one. And this is another great reason for avoiding AT&T syntax, is because telling what's a suffix and what's part of the mnemonic and then looking up the right thing in the documentation is kind of hard. Yes?
Just a comment from slide 1, slide 2. I think that just in general, the version 2, oh no, it was like way later, like near the end.
Oh, slide 1, slide 2.
Sorry, I meant the 2 versions of plus equal.
Oh, this one.
Yeah, so the second version.
No, sorry, I've lost it. That one.
Yeah, so the second version won't qualify for RVO. So in general, it will, I mean, regardless of what happens, it will not be optimized as well as the first one. Just a comment.
So the comment is the second one's not available for return value optimization. Yeah, and the reason is because it's a reference that's coming in. So it's an L. Well, it's effectively it's an L value, so it needs to be copied.
Right. But I mean, even if it was the same one, like if the compiler looked inside the plus equals and it still was returning a reference to the same one, it still wouldn't be allowed to perform RVO.
Yeah, that's true.
So
I think
it would have to like do it under the as-if rule, which is pretty difficult for most classes. So probably never going to get as good assembly.
Probably not. Although, I don't know, I'd be quite optimistic if it's in the same file, and yeah, maybe as if.
It's a very simple class.
Yeah. I had another demonstration I didn't have quite time for, and I was having a look at if you have instead of a const reference, if you had an R value reference because you overloaded, because you wanted to be able to add something that's temporary on the left. Did something similar here, and interesting, I got a difference as that one could be copied and one could be moved in a sort of similar analogy thing. It's very complex, and Nico Jasutis is a much better expert than me at that sort of stuff. Yes?
I think here you could actually have some more optimization if you just pass the first parameter, apply a value, and then just add on to it. So just do an A plus equal B and that. Laser B.
So the observation is if you take the first parameter by value in your operator plus, then you've got more room for optimization. So the answer is maybe.
I think you can benefit from this if you pass in, if you can move the operator, first parameters into your function.
Yeah, it kind of depends. If you've got some, if you're adding something that's genuinely an R value, then maybe. But on the other hand, if you're adding something, if you've got something that's an L value anyway, so you've got a local variable already for some other reason, then you're just moving a copy from inside to outside. So, and if you do move that copy outside, then you don't get the RVO, the NRVO in the top one. So it varies. So thank you very much. That's all we've got time for. But you can kind of like hassle me afterwards, and do go and see our stand just downstairs from here. Thank you.